Hello and welcome to this video lesson. In this video lesson, we will be looking at how we can find average velocity, instantaneous velocity, and displacement from graphing techniques and how we can use certain graphs to extract certain informations from it. Alright, in this video we're going to be looking at a few things. So we're focusing on graphical techniques, and graphically we want to determine how we can find average velocity, instantaneous velocity, displacement, how to describe motion, and how to convert a position time graph to a velocity time graph. One way to talk about average velocity is that it is the average rate of change of position with respect to time. So let's look at this graphically. So let's imagine that we have a graph which has position on one section with a direction and time on the other axis. And here's the graph. And we want to find the average velocity. So to find average velocity, we need to find the average rate of change of position. Position is here, with respect to time, which is down here. So to do this, average rate of change from our previous videos can be found by the slope between 2 points. So we simply take 2 points where we want to figure out what the average velocity is between those 2 points. We draw a straight line to it and we find the slope of that. What does the slope show us? Well, let's see. For the slope here, it is equal to rise over run. Let's say we have 2 points here. One of the points, this is from event 1, this is event 2. So at event 1, we have time 1 here. And at event 2, we have time 2 here. And in terms of position, this is our position 1. And this is going to be our position 2. So time 1 and position 1 for the first point, and time 2 and position 2 for the second one. So in order to find my rise, I have to take the second position and subtract it by the first one. So that's d2 minus d1. And to find the difference between the times, I have to take whatever time this is, subtract it by this, and that would give me the time in the middle. So that's time 2 minus time 1. Now this is same as saying that position 2 minus position 1 is the displacement from 1 to 2. And time 2 minus time 1 is the change in time from 1 to 2. Does this remind us of anything? Well, yes, it does. This is the exact same thing as the average velocity. So to find this graphically using position time graph, what we will do, actually I will write it down here, use the slope between 2 points. And to find average velocity, we always need 2 points because for average velocity, we're trying to figure out what was the velocity on average. So looking at this graph, for example, the speed is high, the speed is getting slower and slower and slower, and then it's now going the negative direction, and slope is 0, and then slope gets high again. So if we were to average the speeds throughout all of this path, our average would be the slope of this line, and that's what it is here. How do we find instantaneous velocity? Well, instantaneous velocity is the velocity at a particular time, or we can also use the terminology that it is the rate of change of position with respect to time at a particular time period. Now, notice in the last one, when we were talking about the average velocity, we said the average rate of change, but this is the exact rate of change of position with respect to time. So what we have to do to find that graphically is to draw a tangent. at the points, and then calculate its slope, and that's from lesson 1.5. So let's do an example here. Calculate the average velocity between 3 to 7 seconds. So at 3 seconds, our position is here. At 7 seconds, our position is here. We want the average velocity. That's the slope between the 2 points. So we're trying to find the slope of that line there. We need the rise and the run. So the rise here, imagining this is event 1, this is event 2. This is displacement from 1 to 2. And this is the time between 1 to 2. So for average velocity, we're going to find the slope, and that's going to equal to the displacement from 1 to 2. That's the rise divided by the run. The rise here this is the second position, that's 5. This is the initial position, here, initial position is 3. So we have 5 minus 3. And for our time at point 2 is 7, time at point 1 is 4. So we do 7 minus 4, and we get 2 divided by, this should have been 3, and we get 2 divided by 4. Now, let's say that all the values are good to 2 significant figures. We're only given the time here. Let's imagine even position is in 2 significant figures. So this is going to be approximately 0.50. And my units, I forgot a few things here. This needs to have a direction. I'm going to give the direction north here. And in terms of unit, this is going to be meters per second. And in terms of direction, it's going to be north because it is positive. And that's also just my positive convention, and the slope is also positive. The second question says, find the instantaneous velocity at time 7. So at time 7, we're right here. If I were to draw a tangent, this is not a curve, it's a straight line. And the tangent to a straight line is just that line. So in this case, I'm trying to find the slope of the purple line. So for instantaneous velocity, slope of tangent at time is equal to 7. And for this particular case, I can take 2 points from here, or I can just say that this is a horizontal line. And for a horizontal line, there is no steepness, so the slope of this line is equal to 0. Or you can just say velocity here is equal to 0. That also works. Note that if I wanted to find the average velocity, let's say from here to here, then my slope would be negative, and that would mean that my velocity would be in the negative direction. So negative north or positive south. So whenever your slope is positive, you're going the same direction, you're moving the same direction as your positive sign convention, and whenever your slope is negative, you're moving opposite to your positive sign convention. Now let's discuss displacement. So displacement is a change in position, and to find this from a position time graph, so if I have a position time graph, this is position. Let's say it's got a unit and a direction. Let's say it's east, and let's say time's got second, and let's say this is meters for sake of completion. And if I had a graph, and if I wanted to find the displacement from one point to the other, let's say from 1 to 2, all I'm going to do is I am going to find the vertical distance between them, because this is the displacement. This location here is the displacement at time 1 or event 1, and at time 2, where I'm interested, the position is here, and the displacement is the change in position. So all you have to do is take the position at this point, which will be the value here, and the position at this point, which will be the value here. So we just subtract the two positions. And this is because displacement is change in position. If we were to do this graphically, we have to use, graphically using a velocity time graph, we would have to do something different. We'll talk about the reasons as to why we do this method a little bit later, but what we have to do, we have to use the area under the velocity time graph. And if the area above the time axis will mean that the displacement is positive or in the positive sign convention, and areas below the time axis displacement will be negative. Let's do an example of this. So I'm going to scroll up a little bit, I'll leave this here. Find the displacement of the object below between times 0 to 10 minutes and 40 to 55 minutes. You can definitely do that. Let's give this, let's make this a little bit more complete by giving this a positive direction. Let's give this positive east. So this would mean that any velocities that are above here are in the east direction, and anything below are negative or in the west direction. So the displacement from 0 to 10 seconds will be from here to here, and 0 to 10 minutes, and here it is. So we need to find the area underneath the curve. In this case, our curve is here, and when we say to find the area under the VT graph, we're talking about the area from the line to the time axis. Area from the line to the time axis. Line to here. Line to here. So for the first one, we need the area here. The shape that we have is a triangle. It's got 60, value of 60 here. So it's starting from here to here, it's 60. And the value from here to here is 10. So displacement for 0 to 10 minutes, displacement is equal to the area under the curve. And displacement here will equal to, for base times height divided by 2 for a triangle. So that's 60 times 10 divided by 2. And 60 times 10 is 600 divided by 2, 300. In terms of my units, we can see that this is meters divided by minutes, and this one is minutes. When you multiply these out, I'm going to do it here. Meters divided by minute multiplied by minutes. These two cancel out to 1, and we're left with meters. So my final unit here is simply meters. We're going to do the same thing for our next question. So the next question is the displacement from 40 to 55 minutes, and 40 is right here, 55 is right here. I'm looking at this area, so I'm going to use the area under the curve. You can also say above the curve for this one. I have a triangle again. In this case, we can see that this value here is negative 40, so you can either just use 40 times 15 divided by 2 and then make it negative because the area is underneath the graph, or just use the negative value here. So that's negative 40. I know area can't be negative, but we're just going to use the negative value here. Negative 40 and our base is 15. So times 15 divided by 2. And how much is this? Well, negative 40 divided by 2 is negative 20 times 15. That's negative 300. And the units will be the same as meters, just same reason as to why this was meters. And that's how we find the displacement. We always use the area underneath the graph. And the next question says, calculate the total displacement of the object above. Okay, so in this case, we have to find a few other areas as well. So we need to find the area of, I'm going to color them differently, this area over here. This is a rectangle. We got width of 5, and we got height of 60. 60 times 5 is 300. It's plus because it's above. And then I will use, and let's use a different color. Let's use this blue. This area over here, we got a base of 15, and we got height of 60. So 15 times 60 divided by 2 because it's a triangle. And that would be 30 times 15, which should be 450. Okay, the next area. So what I'm doing now is I'm just finding the individual displacements for each section, and then I'm going to add them all up together. So let's use a different color. Let's do green. And for this section over here, my base is 10, and my height is negative 40. And it's a triangle, so I would have to do 10 times negative 40 divided by 2, and that will be negative 200. So for the total displacement, so displacement total here is going to equal to, basically it's kind of like saying the total displacement is the displacement from here to here plus the displacement from here to here plus here to here plus here to here plus here to here. And we can calculate that by area under entire curve, and that's going to equal to, I have my purple area, which I calculated to be plus 300, and then I had my red one, which was 300, and then I have 450 was my blue one, and then I had some negative ones. I had negative 200 for my green, and I'm doing this in color. You don't have to do it in color, but it just makes it a little bit easier for you folks to see what's happening. And once I add everything together, I will get 550 meters. And I'm totally forgetting all my directions. So I'm going to go back this displacement. First of all of these need the arrows, and the direction east. This can be rewritten as 300 meters west if you wish, but this is fine too. And my final answer is also in the east direction. And in this case, my positive sign convention has to do with the label on my position axis here. So in this case, we're saying that everything here is east and everything in the bottom is south. Is west. Now, you may be asked for the total distance here. So let's do an extra question, total distance. And when we calculate the total distance, we don't care about signs. The negatives are positive. So in that sense, instead of adding any negatives here, we will change them to positives. So in this case, this would become 300 plus 300 plus 450. When we say negative 200 and negative 200, that means the person or the object was moving backwards. In this case, we want, for distance, we don't care if they're moving backwards or not. They are traveling that amount, and we need to include them. So instead of negative 200 here, I'm going to use positive 200, and for negative 300, I'm going to use positive 300. Add them all up, I'm going to get 1550 and meters. And for distance, I don't need a direction. You can see that I have the arrow here for displacement. I don't have it here for the distance. And my final answer here would be 1550. Now, how do we convert a position time graph to a velocity time graph? We are going to use the instantaneous slope. And what I mean by that is slope of tangents. Let's do a few practice and hopefully this will help you. So right at the beginning, I'm going to actually choose a few points. In this case, I'm going to choose just 3. Sometimes we need to choose more points, and with more experience, you'll kind of get better and better with that. So right at the beginning, a huge common misconception is that right at time 0, our slope is always 0. It's not. In this case, you can see if the line was to continue, the slope will also continue in this direction. If I were to take a tangent at this point, I'm going to draw my tangents using pink so it's a little bit easy to see. You can see that the tangent, because it's a straight line, it's just straight line. Tangent here, straight line, tangent here, straight line. So in all of these cases, the tangents will look exactly identical. Now, when we want to find the velocity, instantaneous velocity can be found by the slope of the tangent. So there's two things we need to consider. One is that the slope, is it positive or negative? If it's positive, it will be plotted in this region. If it's negative, it will be plotted in this region. This slope is positive, positive, and positive, so we're dealing with this section of the graph. Now, the slope, I'm just drawing this. If we had values, we would actually find the slope values and then plot the exact numbers. In this case, we're just going to go based on whether this, we're going to sketch it. We don't have to draw it out, so we don't need exact numbers. So we're going to approximate. This is a slightly low slope. It doesn't seem to be too steep. And if it's not too steep, the value of it is going to be pretty small. So the velocity isn't too large in terms of value, and it's positive. So slope, small number, positive, small number, positive, small number, positive. And the values you can see, because the slope isn't changing, velocity isn't changing. So the value of the velocity is going to stay the same throughout the whole time. Now, let's look at the next question. The next question, we're going to choose 3 points again. And let's do purple. Draw some tangents. Tangent, tangent, tangent. In this case, the slopes, we can see the slopes aren't changing throughout the whole time. So the velocity isn't going to change. The velocity is going to be a straight line. In terms of the slope, the steepness is much larger than before, so the value is going to be large, either positive large value or a negative large value. And in terms of a sign, the slope is positive, and if it's positive, the velocity is also positive. So we're dealing with this region of the graph. Since the value of the slope in the first point here is large due to the large steepness, then I'm going to plot a large positive value for the slope. The slope at the second point is exactly the same as positive large value, exactly the same as the last one, and that slope doesn't change throughout, so the velocity of this object is constant. So you can see that whenever the position time graph has a straight line, the velocity will be consistent. It will not change. So the velocity here always stays about the same value because the instantaneous rate of change of position with respect to time is consistent throughout this whole graph. Now, let's do the next graph. We're going to plot a few points. I'm going to use purple again. So we're going to have the first one. Let's do a couple of points here. Someone's going through a 0, so I'll do that, that, and that. First of all, we have a straight line on a position time graph. We should have a consistent value somewhere here. Let's draw a few tangents to get an idea. Tangent right here. Tangent right here. For a straight line, the tangent is just that straight line. And for all of these, we can see that the slope value is pretty steep. So the value is going to be pretty high. Small values are close to 0, and large values are close to infinity. And in terms of sign, it's negative. It's a negative slope, so I have to deal with this region of the graph. Since the steepness is high, then my slope is that means that my velocity will also be a large number. So in this case, in the beginning, for the first point, the steepness is large and the sign is negative. For the second point, the steepness is large, it's negative, and the same steepness in this one, so we have the same value, same steepness, same steepness, same steepness throughout this whole region. So this will be a nice consistent velocity. It's negative in direction, meaning that the object is not moving in the east direction, it's moving in the negative direction. And you can see that the position is initially to the east of our reference point, and the object is moving towards the reference point in the west direction and then continues to go to west. And this is saying that the velocity, the movement, is always towards the west direction. Okay, let's do some more graphing. In this case, we have some curved graphs, so this is going to be very nice. I'm going to draw a few lines in here to give me an idea. So here, here. You can do as many points as you want. The more you do, the better it is. Usually I definitely do a few I definitely do one at the beginning and at the end, and then some in the middle. I'll do my lines for this one as well, and then I'll kind of get started. Okay, now I have a good number of points. Let's draw some tangents for the position time graph. Starting here, the tangent is pretty steep. Less steep, less steep, less steep, kind of flat down there. Okay, let's think about what we're going to do with the slopes here. So first of all, the first one, the steepness of the line is very large and the value is positive. I'm going to go right in this positive section here and draw a line that because the steepness is high, I'm going to use a high velocity value. In the next section here, the steepness has gotten much smaller and it's just getting smaller and smaller as we go, and it's all positive. So I'm going to actually draw some other, yep, so the slope is decreasing, 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 and decreasing. And at the end, you can see that the slope is pretty flat. And when it's flat, that means there is no steepness and there is no velocity there. So now I'm just going to connect the lines. In this case, I kind of wanted to make it a straight line, so I'm going to kind of say that the slopes are kind of like this, and we kind of get a straight line like that. There is possibilities that this one is very large, and then this one gets much smaller, so you get a curve like that. But basically, if you had the numbers, you could check. In this case, we're just sketching, so it doesn't really matter. I just want to make sure that my students are able to recognize that they have to draw tangents and that the slope of the tangent will tell you exactly what the velocity is at that time period. For this one, right at the beginning, the slope is pretty kind of like flattish. It gets negative, but the value is small. So in the beginning, we're kind of here, and then the value kind of small slope here. And then right about here, the slope is getting a little bit steeper, not too much, something along this line. It's getting a little bit steeper right here. It's still negative, the slope is negative, and then it's getting a little bit steeper there in terms of my tangent. So kind of like here, and finally it gets quite steep there. So it kind of looks something like this. And if I connect the lines here, we can see that in this case, the velocity of the object is actually increasing. So there's a huge misconception. Sometimes students think that because it's going in the negative direction, it's actually decreasing. That's not true, because small numbers are close to zero and large numbers are close to infinity. So in this case, the velocity starts at zero, starts to increase in the negative direction. This just means that the object is moving in the west direction, and it keeps going in the west direction, and its velocity in that west direction is increasing. So initially, again, in terms of if you look at the position time graph, the person was standing right at the reference point, and then they started moving towards the negative directions of east, which is west. So through this whole time, the person was moving in the west direction, and we can see that even on the graph, the person was moving in the west direction. So what are the steps again to do this? Choose a few points on your position time graph, draw their tangents, and the slope of your tangent will determine the value of your velocity. So for example, here the first value was a very steep one and positive. That value was positive, and steep means large. This value here, the very last one, was flat, meaning the value was zero right away. And same thing here, in the beginning it was zero, and then we got steep and we got negative values. So that's kind of represented there. Okay, finally, how about describing motion? So in study of motion, it is important to be able to quantitatively and qualitatively determine the meaning of different types of graphs. So let's start with the position time graph and kind of tell you what information you can extract from this. So in this one, you can see first of all, in terms of this is the starting point, this is the end point. So in starting point, the person or the object is at the reference point. So starts at reference point, and this person is, or this object, sorry, is first at the reference, and then they're moving in the positive direction of position. They're moving in this direction with time. So that means that this person is moving in the east direction. So moves towards east. Now, what else can we know about this? Well, we can see that the line is straight, and that means that the person pretty much every unit of time, the person travels the same amount. And if you were to draw tangents here, you can see the speed is always the same, because the steepness of the line is always the same. So this is moving at constant velocity. Can we know anything about the speed? Well, yes, because the tangents, the direction of the slope tells us the direction of movement, in this case east, which we also figured out by the position, but also it tells us the steepness of the line tells us how large the velocity is. So in this case, especially comparing this with this, qualitatively, we can kind of say that this is relatively slow speed. So I'm just going to say relatively low speed. And we know this based on the steepness of the line. We know constant velocity because it's straight line. We know that it moves towards east because it's a positive slope and starts at the reference point. We know that because it starts at the reference point. And the reference point is this time axis represents our reference point in terms of our position time graph. Now for the next one, again, it starts at the reference point. Again, it moves east because it's a positive slope. Again, it's constant velocity because it's a straight line. In terms of speed, though, in terms of the steepness of the slope, it's much higher. So I'll call this A, B, C. So A, B, and C all apply here, but the next point doesn't because in this case, relatively high speed, and that's because the steepness is high. Okay, we're gonna look at our last two graphs for today. The first one, again, is position time graph. This time, we are not starting in the reference point. So at time 0, we are in the east of our reference point. So start from east of reference point. We move towards west. Because what's happening, you can see we start in this direction. This is the reference point. This is the east of reference point. So if we went this way, then we would be moving east, but in this case, we're moving in the west direction. So we move towards west. In terms of, we can kind of mention that we reached the reference point and then we move west of it. We can add that information if we wanted to, but let's talk about velocity a little bit here. So from here, we can see that if we were to draw tangents, all of them will be the same. And since we have a nice straight line, we are moving at a constant velocity. Okay, good. It's constant velocity. In terms of values, is it steep? This is pretty steep, I would say. So since it's steep, it's a relatively large velocity. I'm just going to say since steep. And in terms of direction, again, moving west, we can know that from position time graph because of the direction it's moving, but we can also know that based on the slope. Because the slope is negative, it means that the object is moving in the west direction. And those are the information we can extract from this graph. Finally, we have this lovely velocity time graph over here. And what do we know about this graph? I'm not going to write all of them down because we're going to go into a lot more detail with velocity time graphs later. But what we do know about this is initially we have a very large velocity, so the object is moving very, very fast, and they're moving in the north direction. So anything in this region of a velocity time graph is when object is moving north, and anything in this region is when the object is moving in the south direction or negative north. So that much we know. We know the object initially is going fast. We know the object is kind of changing their velocity. They're getting slower and slower and slower and slower. At this point, the velocity value is 0, and then in these regions, velocity values are negative. So that means the object has slowed down to 0 and then started moving in the opposite direction, and the object started speeding up and going faster and faster and faster and faster as time has passed. So we have no information about the initial position of this object, so we don't know whether the object was initially at a positive location or a negative location. This graph does not give us those information. All this graph will tell us is what are the values of velocity during the time period that the object was traveling. And we can use the areas underneath this graph to figure out our displacement but again, we don't know what that initial position was. And that's where we're going to conclude this video. Don't worry about this section. You can just, if you kind of understood what I said, that's good. That's planting a seed for future lessons. I hope that this lesson was helpful for you folks, and I hope that you have a wonderful day.